Welcome to session 10 of Digital Electronics Problem Solving course on IEEE. I am Sachin Sampath, your instructor from the Indian Institute of Science. We stopped the last session at problem 5.11. We'll continue now from problem 5.12. There are three parts in the question. First is a state diagram. Second is the reduced state table. Third is the state diagram corresponding to the reduced state table. There are 8 states. A, B, C, D, E, F, G, and H. When input is 0, A goes to F. When input is 1, A goes to B, with output 0 in both cases. B goes to D and C with output 0. C goes to F and E. D goes to G and A. E goes to D and C. F goes to F and B. G goes to G and H. H goes to G and A. That is part A, the state diagram for the given state table. Next, we have to tabulate the reduced state table. We can see that and B and E are equivalent because they both go to the states D and C when input is 0 or 1, and they both give the same output 0 0 for input 0 and 1. So B and E are equivalent. D and H are equivalent. D and H, B and G, B and E. So now the state will reduce to, I'll copy this. So I can remove the row containing E, and I can remove the row containing H. And wherever there's an E, I can replace that by a B. And wherever there's an H, I can replace that by a D. Now again we can see that A and C are equivalent because B and E are equivalent. So in the next stage, say A and C are equivalent. So now you can remove the C, row containing C, and wherever there's a C you can replace that by A. That's it, and there's no further simplification that we can do because except for FB, all the other states are different from each other. And in when present state is A or F, the next state is FB, but the output is different. If it's in A, the output is 0 0. The present state is F, the output is 1 1. So we can't reduce this any further. This is the reduced state table. C asks us to draw the state diagram corresponding to the reduced state table. So part C, there are only 5 states. A, B, D, F, and G. A will go to F and B. B will go to D and A. D will go to G and A. F will go to F and B. G will go to G and D. That is the state diagram of the reduced state table. So there are far fewer states. There are three states less than the state table before reduction. That was problem 5.12. Next is problem 5.13. There are only 20 problems in this chapter that are not related to HDL or Verilog. Lot more problems related to Verilog and HCl that I won't cover. They're asking only for the output sequence given a particular input sequence, and the particular input sequence is 0 1 1 1 0 0 1 0 1. We start out from state A. For input 0, output is 0, we go to state F. Go to state F with output 0. Then there are three ones. If you give a 1, F goes to B with output 1. F goes to B with output 1. Then B goes to C with output 0. And C goes to E with output 0. Then there are two zeros. From E, if you give a 0, you get D with a 0 output. At D, if you give a 0, you go to G with output 1. Then there's a 1 followed by two zeros. There's a 1 from G. If you give a 1, you go to H with output 1. Go to H with output 1. And from H, you give a 0, you'll go to G, and another 0 will keep you at G with outputs 1 and 0. Go to G, stay at G with output 1 and 0. Then you give two ones. So from G, if you give a 1, you go to H with output 1, and if you give a 1, you go to A with output 0. So you go to H and then to A with output 1 and output 0. So the output sequence is 0 1 double triple 0 triple 1 0 1 0. Now we do the same thing but with this reduced state diagram. You start out with A, input is 0, so you go to F with output 0. Then you have three ones. From F, a 1 will send you to B with output 1. From B, a 1 will send you to A with output 1. From A, it will send you to A with output 0, sorry. So there are three ones. The first one sent you to B, second one sent you to A, and the third one will send you back to B with output 0. Goes to B with output 0. And there are two zeros now. From B, if you give a 0, go to D with output 0 and then G with output 1. So D to G with output 0 and 1. Next, a 1. From G, if you give a 1, you go to D with output 1. And two zeros, you go to G with output 1. And you give another 0, you stay in G with output 0. So you go to G with output 1 and you stay in G with output 0. Then you are given two ones. So from G with 1 1 you'll go to D and the other one you'll go to A with output 1 and 0. So the output sequence is the same. So reducing the state table doesn't change the output sequence, or it will only change the states that are available. And the state transitions will also be equivalent up to equivalency between the states. So from P, here you go to C, but here you go to A, but C and A are equivalent states. And from there, C you go to E, here you go to B, but those two are equivalent states, E and B. So you are actually going either to the same states or to equivalent states. That's problem 5.13. We'll go to problem 5.14. There are two tables they are talking about, table 5.9 and 5.8. Let me see what those tables are first. Table 5.8 is as follows. It's a reduced state table. We have present state, next state for a single input, which can be 0 or 1, and the output depending on the input. There are 5 states. And table 5.9 is as follows. Three possible binary state assignments, of which assignment 3 is the one hot assignment, which assigns A, B, C, D, E to the states. It's called one hot because only one of the bits in the binary number is high in each state. So if we substitute the states in table 5.9, we get the binary state table. So the solution For A, we'll substitute 0 0 0 0 1 0 0 0 1 0 0 0 1 0 0 0 1 0 0 0 1 0 0 0 0 0 uh, 1 followed by 4 zeros. Now A, B, C, D, A, D, E, D, and AD. That's it. That's all they're asking for. Problem 5.15. List Figure 5.12a is as follows. It's a D flip flop. converted to a JK flip flop. We are asked to write the table for the JK flip flop. We have Q of t, Q of t plus 1, Q of t inputs JK, Q of t plus 1. The state can be either 0 or 1, present state. The inputs can be 0, 0, 0, 1, 1, 0, or 1, 1. If the inputs J and K are 0, 0, then the state is preserved as is. So you will get a 0 here. Q of t plus 1 is nothing but Q of t, which is 1. The input is 0, 1, then you will get a 0 at Q of t plus 1 will be 0. So Q will be 0 after a clock pulse. The input is 1, 0, you will get a 1. And if the input is 1, 1, it will toggle. So if Q of t is 0, Q of t plus 1 will be 1. And if Q of t is 1, Q of t plus 1 will be 0. From this you can write an excitation table. This will give you Q of t plus 1 is equal to J bar K plus J Q bar. And we can see that the input to the D flip flop is J bar, JQ bar plus, sorry, I might have made a mistake somewhere. Sorry. So the way I've filled the table up is by taking Q on this side and JK here. So the expression is actually J Q bar of T plus K bar Q of T. So that is what is given as the input to the D flip flop. So after a clock pulse, the D flip flop gives out whatever is there at the input as the output. So the output will be J Q of T plus 1 will be D of T, which is J Q bar of T plus K bar Q of T. We'll go to problem 5.16. I'll only solve part A, part B will be left as homework because it is very similar to part A, only the state transitions are a bit different. So we'll find the input to the so here we have D flip-flops, and in D flip-flops the output of the next state is the same as the input at the current state. So if you want to get a particular output in the next state, we have to give that as the input in the current state. So dA and dB will be nothing but A of t plus 1 and B of t plus 1. So if we have the present state A of t, B of t, and input x, next state A of t plus 1, B of t plus 1, which is nothing but dA at time t and dB at time t. We need to give whatever we want in the next state as the current state, or current input to the D flip-flops would be the proper framing. There are four possible states: 0, 0, 0, 1, 1, 0, 1, 1. When the input is 0, the state has to be preserved as it is. So we'll get 0, 0, 0, 1, 1, 0, and 1, 1. When the input is 1, the following transition should happen: 0, 0 should go to 0, 1, 0, 1 should go to 1, 1, 1, 1 should go to 1, 0. Sorry. 1, 1 should go to 1, 0. And 1, 0 should go back to 0, 0. We can solve this using K-maps and we'll end up with dA is nothing but ax prime plus bx, dB is a prime x plus bx prime. When x is 0, dA is a, when x is 0, dB is b. So the previous state is maintained. When x is 1, dA is b, which is what occurs when x is 1, you have 0, 0, x is 1, you have 1, 1, x is 1, you have 0, 0, x is 1, you have 1, 1. So dA follows B when x is 0. When x is 1, and dB when x is 1 will be equal to A prime. We can see when x is 1, A is 0, dB is 1. A is 0, dB is 1. A is 1, dB is 0, A is 1, dB is 0. You can do the same thing with the second part. I'll leave that as homework. In the end, you will get dA is A prime x plus AX prime, which is A XOR x. dB is AB plus BX prime. Could take the B common and write it as B times A plus X prime. Problem 5.17. They want us to implement a serial two's complement. Two's complement. So if you give a 0, it should give two's complement, which is a 0. You give a 0 0, it should give its two's complement 0 0. Suppose you have a 0 0 1 at some point. Initially, suppose you give a 1, two's complement of 1 is 1. If I give a 1 1, two's complement of that is 0 1. If I give a 1 1 1, two's complement of that is 0 0 1. If I give 0 0 1, two's complement of that is 1 1 1. So until the first 1 occurs, the output should just be 0. Afterwards, when the first 1 occurs, the output is 1, and after that, whatever occurs should be complemented. Suppose 1 occurred right at the beginning, you have 1 and you're done. Suppose you got 1 1, so this is the first occurrence of 1, so that should give you output 1, and all the next input bits are complemented, so 1 is complemented to 0. Suppose instead of 1 1 you got a 0 1, that is the first bit was 1, so you'll get a 1 here, then the next bit is 0, should be complemented 1 1. So that is actually the 2's complement of 0 1. Similarly, suppose you start out with 0, as long as it's 0, its 2's complement is just 0, and then the first 1 occurs, first 1 occurs, let's say at some point 1 0 0. The 2's complement of that is 0 1 1 1 plus 1, which is 1 0 0. So now these are all zeros because before that no 1 has occurred, and then when the first 1 occurs you have a 1. Suppose next you get 0 1 0 0 0. The complement of that is 1 0 1 1 1 plus 1, which is 1 1 0 0 0. So up to here there is no 1, so they're all zeros. And the first 1 occurs, you get a 1. After that everything should be complemented, so this 0 is complemented and you get a 1. Suppose you got 1 1 0 0 0 instead, its complement is 0 0 1 1 1 plus 1, which is 0 1 0 0 0. So up to the first 3 bits there was no 1, so they are just zeros. When the first 1 occurred, the output is 1. Then every bit should be complemented. So the logic is, when you are giving serial inputs, up to the first one, if you have any zeros, the output is 0. When the first 1 occurs, the output is 1. And then every bit has to be complemented. So what does it mean for the first one to occur? It means that the previous state must have been a 0, because if the previous state was a 1, then that would have been the first one to occur. So first for the first one to occur, the previous state must have been 0. And for all zeros occurring after this first one, they're all complemented, so you should get a 1. So if the previous state, so state 0 is the state where no one has occurred, and in state 1, okay, there are two states. In state 0, the output will be the same as the input. State 1, the output will be complemented. It's the complement of the input. Let's try to write the state diagram for that. So the two states are before a 1 has occurred and after a 1 has occurred, or when a 1 has occurred. So before a 1 has occurred, if you're in the state where a 1 hasn't occurred yet, if a 0 occurs, then you stay in that same state. If a 1 occurs, you go to the state where 1 has occurred. And the output should be a 1. Because when the first 1 occurs, the output is 1. So if it's in the first state and the input is 0, next state is still 0, output is 0. If it's in the first state with input 1, next state should be state 1 with an output 1. Now it's in the state 1 has occurred. Since 1 has already occurred, if the input is 0, you should get, it should still stay. After 1 has occurred, you can't go back to the state where 1 has not occurred. So the next state will be 1 always, regardless of the input. Only thing is the output is the complement of the input. So that is the state diagram, which will give you, if you are implementing with a D flip-flop, D is equal to A plus X. This is the OR gate. And in a D flip-flop, if you want the next state to be something, you give that as the input to currently. So you give the OR of present state and input to the D input, and then the output is the XOR of A and X. So the circuit implementation is as follows. You have X, we have A, the output is the XOR of A and X. And they want an asynchronous reset button. If you want to the state diagram, then it's in state 0 where a 1 has not occurred initially. If a 0 occurs, then a 1 has not occurred, so the output is 0. If a 1 occurs, it goes to the state where 1 has occurred, and the output should be 1. Because the output corresponding to the bit where the first one occurs is always a 1, as I saw in the previous examples that I showed. And once it is in state 1, it can't go back to state 0 unless you reset that. Reset. If you don't reset, then it will simply keep complementing the input and giving that as the output, and it will stay in the state where a 1 has already occurred. Problem 5.18. Three more problems left. This is similar to the previous problem except that there are two flip-flops, and instead of D flip-flops we have JK flip-flops, and instead of one input we have two inputs E and F, and different stuff happens for different input combinations of E and F. So E can be regarded as the enable input. Have the present state AB, inputs EF, next state A of t plus 1, B of t plus 1, and here there's a small change because we are using JK flip flops instead of D flip flops. The excitation is different. So the excitation table was for a D flip flop, whatever output you want, you should give it that as the input. Whatever output you want in the next state, that should be the input in the present state. But that's not true for the JK flip flop. You have to specify the flip flop inputs to get a particular state. And there are two flip flops A and B. So I'll name the inputs as JAKA and JBKB. There are 16 possible combinations here. For the present state and the inputs. So the present state could be 0 0. Corresponding to that, the inputs can be 0 0 0 1 1 0 or 1 1. Similarly, input state, present state can be 0 1. And the inputs can be 0 0 0 1 1 0 1 1. Present state can be 1 0. Corresponding to that, input state can be 0 0 0 1 1 0 1 1. And the present state might be 1 1, and the inputs might be 0 0 0 1 1 0 1 1. Now if E is 0, the state has to be maintained as is. So whenever E is 0, you can write down the next state to be the previous state itself or the present state itself. When E is 1 and F is 1, circuit goes through the state transitions from 0 0 to 0 1 to 1 0 to 1 1 and back to 0 0. So when F is 1, 0 0 goes to E is obviously 1 now. After E is 1, if F is 1, 0 0 goes to 0 1, 0 1 goes to 1 0, 1 0 goes to 1 1, 1 1 goes to 0 0. And When E is 1 and F is 0, the circuit goes to a different cycle. From 0 0 it will go to 1 1, and then from 1 1 it goes to 1 0. From 1 0 it goes to 0 1, and from 0 1 it goes to 0 0. So that's the state table. Now using the excitation table of JK flip-flop, we can write the necessary inputs. So from 0 0 to go to 0 0, you can give 0 at JA, anything at KA, 0 0 0 1, both will work. So it's a don't care. That comes directly from the excitation table. Similarly, B, for it to go from 0 to 0, JB, KB can be 0x. In a similar fashion, if you fill out, so it will be 0x whenever there's no change happening. Whenever 0 goes to 0, there will be 0x. So here and here, here and here, sorry, only there and here. If it's going from 0 to 1, you should give 1x. 0 to 1 1x, 0 to 1 1x, 0 to 1 1x, and 0 to 1, 0 to 1. Let me write that down again. I think I've made a few mistakes. So if the state goes from 0 to 0, then you need to give the input to the JK flip-flop as 0x. So there's a 0x here. First I'll do for the A flip-flop and then go to B flip-flop. So 0 to 0, 0 to 0, 0 to 0, that's it. For the B flip-flop, you have 0 to 0 in the first two places, and zero x is there. Okay, that's it. Then if it's going from 0 to 1, you need to give input as 1x, 1x, 1x. That's it. In the second flip flop, 1x, 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 and 1x. And if it goes from 1 to 1, you can give either 1 0 or 0 0. So it's x0, 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 x0. Similarly, x0 here, here, and those two places. Now if it goes from 1 to 0, you need to give either it should toggle 1 1 or it should clear 0 1. So it's x1, 1 to 0 is x1, and in the other table, remaining places have transitions from 1 to 0, it's x1. Now you take the inputs column as the input, EF, now you take the input column as well as the present state AB. So AB and EF as the inputs to get functions for JA and KA, with the x's all being don't cares here. And then you simplify that using a K map. And you will end up with JA equals bx plus b prime x prime e, Ka is bx plus b prime x prime e, and JB is equal to E, KB is equal to E. I can verify one of those for you. Let me just show for JA and you can do the rest yourself. Here you have AB, you have here you have EF, and last 8 are all don't care. For JA, this is, you have only a 1 for 2 and 7. So 2 and 7. Sorry, this is not X. Our inputs are E and F, so this should be F. So this is EBF. This is EB prime F prime, which are the two terms present here. If you distribute it, it will become EBF plus EB prime F prime. If you look at KA, then the same thing happens, except that for KA, all the x's occur at the top, and this pattern of 1x, these two ones will occur at the bottom part. But since the map is kind of symmetrical, so this entire thing will be flipped kind of, right? But in the end, this x will come here and this 1 will come here, this x will go here and that 1 will come here. So the pairing doesn't change. You'll have the same pairs. That's why you have the same boolean expression for both of them, J and K. Let's do this for JB also, and KB you can do it yourself. For JB you have 0 0 1 1, so 1 1 there, then XX, these are x's, then 0 0 1 1 again, which is 1 1 here, and 4 x's. So you can form a an octet, and that will remove f prime, f and f prime, and that will remove all these terms, a and b. So you'll be left with just e. So JB is equal to e. Similarly for KB, you see that the first 4 are x's. So the top line will be full of x's, and the last 4 boxes will also be x's, and the ones will come here. So again you can, and you'll have x's here. So again, you can form the same octet, and you'll get the same expression. So that's all you need to do. Now you just need two JK flip flops. Connect J, A, and KA to the same through a combinational circuit through OR and AND gates to BFE and B prime F prime E. Connect JB and KB to E, and you will get the desired circuit. Two more problems in chapter 5, and then in session 10 we'll cover chapter 6, session 11 we'll cover chapter 7. That's the state diagram. And then the question is, So it's a circuit design question. There are three unused states: 101, 110, and 111. One input and one output. Have the state ABC, the next state A of t plus 1, B of t plus 1, C of t plus 1, the output Y, X in, Y out. So 000 will go to 011 with output 0. 000 for input 1 will go to 100 with output 1. 001 for input 0 will go to 001 itself with output 0. And if the input is 1, it will go to 1000 with output 1. State 010, 011, 100. Those are only valid states. From 010 you go to 010 or 000. From 011 you go to 001 or 010. From 100 you go to 010 or 100. The outputs will be 0101. They'll keep alternating. That is, they follow input X. So if the input is 0, output is 0, and if the input is 1, output is 1. Actually, that's not correct. Let me check. If there's a mistake in the... Okay, the diagram is correct. That means that from 100, if you give a 1, you go to 011. Okay, there might be let me check all the states first. From 000 you go to 011 or 100. From 001 you stay in 001 or go to 100. From 010 stay in 010 or go to 000. From 011 you go to 001 or 010. From 100 you go to 011, 010 or 011. So from 4 you don't go to 4. The final line is wrong. So 100 you actually go to 011 with output 0. So that's the state table giving you the present and next state and the output given a particular input and present state. What do they want us to do? Um, there are a few more states which are all unused. So 101, 110, and 111, regardless of the value of input X. These are don't cares. Don't cares for the output side as well. Then simplify using K-maps, that's it. You'll get dA is A prime B prime X, dB is A plus C prime X prime plus BCX, DC is CX prime plus AX plus A prime B prime X prime, and the output Y is simply A prime X. For part B, I'll leave that as a homework. You just need to write the inputs J, K, and X to this, X to Y out, and use the excitation table to write what inputs you need to give for which state transition to happen. So, final question in chapter 5 that I will be solving. Of course, there are more questions, all based on Verilog. Design the sequential circuit specified by the state diagram above using T flip flops. So we had to do it with D and sorry, it's T flip flops. It's not the above circuit. It's figure 5.19. The above circuit is called figure P 5.19. So it's a figure from a problem, but they're asking for figure 5.19. So I'll have to draw figure 5.19 for you. So the state diagram is as follows. From 0 0 you stay state 0. If the input is 1, go to 0 1 if the input is 0, which is called state S1, which goes to state 1 0 if the input is 1, state 1 1 if the input is 0. This is called S3, this is called S2. In 1 0, it stays in 1 0 if input is 1, goes to 1 1 if input is 0. from 1 1. With input 0 it goes to state S0, otherwise it stays in state S3. From this you can write the present state, input, let's call this present state AB, input X, next state after 1 clock pulse, and the toggle inputs T and TB needed to get the required state transition. So state 0 0, 0 1, 1 0, 1 1. From 0 0, it will stay in 0 0 for input 1. It will go to for input 0 it goes to 0 1, input 1 it stays in 0 0. From 0 1, input 0 it goes to 1 1, input 1 it goes to 1 0. From 1 0, input 0 it goes to 1 1, input 1 it stays in 1 0 itself, and from 1 1, input 1 it stays in 1 1, input 0 it goes to 0 0. For if TA is 0, the previous state is maintained. If TA is 1, it is toggled. So if you want to go from 0 to 0, we need to give TA is equal to 0. If you want A to go from 0 to 1, you have to toggle it, so TA should be 1. If you want A to go from 1 to 1, then it should maintain the state, so TA should be 0. If you want 1 to go to 0, then you should toggle it. So you only toggle whenever you need the state to go from 0 to 1 or 1 to 0. For TB, 0 to 0 and 1 to 1. Here you have a 1 to 0, 0 to 1, 1 to 0, and a 0 to 1. From this you can write the K-map. With A, B and X for TA and for TB. TA you have a 1 in these 3 places, which gives you 2 pairs, which gives you TA is equal to, from the pink pair you get A prime B, from the blue pair you get Bx prime. So it's B into A bar plus X bar. TB you have 4 ones, 0 0, 0 1 1, 1 0 0, and 1 1 0. So You have one pair here, the second pair, and the third one is left as is. You can't group it together with anything else, so you get an expression with three terms. The pink pair will give you b prime x prime or b bar x bar. The blue term will give you, blue pair will give you a x bar, and the orange unit will give you a bar bx. The logic diagram for this is up to you as homework. So with this we finish session 10 and also chapter 5. So we'll meet in session 11 to cover chapter 6, and in session 12 we'll cover chapter 7.